our depth was the lemma. Our domain, we covered everything into 2 covers, and there was function h on black, function h on white. So there was lemma which says that Laplacian of h on, so what was roughly speaking the situation, that there was a function h on white which is bigger than function h on black, and then there were harmonic functions with the same boundary values, hb star, h white star. And we used in this whole logic to show that there are 2 functions which are sandwiched between harmonic ones. The fact that, well, I mean, first of all, that we already had arithmetically, h white is at least h black just by definition, that Laplacian of h white is positive and Laplacian of h black is negative. So let's prove it. I don't think I will give the full proof. I will just explain how one can calculate that this is true. First of all, maybe I'll note that 1 is more or less equivalent to 2, because what was here the definition? The definition was that h white minus h black is equal to f, absolute value of f squared, on the h in between them when we jump. So so if we jump from black to white, we increase. So if we jump from white to black, we decrease. So in a sense, one can switch from h white to h black by just taking the negative. So if one is subharmonic, the other is superharmonic. So we can just go from hw hb, we can go to minus, well, let's say minus hw minus hb, and there will be all the same properties. So it's if delta h white is positive, then delta hb is also, delta minus hb is positive, so delta hb is negative. So essentially it's enough to prove one of these. Now suppose that we have some place where we want to prove it. So let me maybe denote this point by z and the point surrounded by whatever p, q, r, and s. So z is let's so that it's signify that it is a white point. Let's denote it by white. So there is a stronger lemma. So it's so apparently Laplacian of function h at point w can be written in terms of f, and not to get the constant wrong, I will look it up. So it can be just written as f of p minus f of r, absolute value squared. And there is a constant in front, which is not important. Yeah, I think the constant is just equal to 1. Yeah. So for white, it's and this is also by symmetry, because f is discrete analytic. This difference is equal to this times I. So this is equal to fq minus fs squared. So this just because f is discrete holomorphic. So I won't do the full calculation. I will just make, first of all, an observation that we can calculate this in terms of these two numbers. And the reason is very easy. So what is HW? It's the sum of increments like this, like that, and like that. So it's sum of 4 increments. So this increment is just f of p, imaginary part or real part, so it can be written in terms of f of p. This increment is f of r, so it can be written in terms of f of r. Now this increment is f of s. Now for f of s, we know projection on these two lines, which are just written here. And if we know these projections, we know f of s. So f of s, or this increment, can be written in terms of numbers which are on these two edges. But numbers on these two edges are projection of this one and projection of that one. So it also can be written in terms of these two. So everything can be reduced to these two. And one can even argue, so it's, well, I mean, let's do a proof. So, well, I will do 2 proofs. I will start calculation. But before, I will just argue that, well, first we can write Laplacian of HW in terms of f of p and f of r. So that is clear. Now, since all increments are quadratic, we'll get some quadratic form. So this will be a quadratic form in terms of f of p, f bar of p, f of r, f bar of r. So some combination thereof. And now actually one can observe some symmetries. So first it is symmetric when you rotate by 180 degrees. So it's symmetric when r and p are exchanged. Okay. And it's less immediate, but it also does not change when you add a constant. So it's so there are other symmetries. So it's preserved by f plus constant. So it's a bit more difficult to see, but basically you can write a list of properties which will just tell you that it has to be this form. So this form, for example, is symmetric when p and r are exchanged, and also doesn't change when you add a constant. The only other thing which you can also add a term f bar minus f bar, but that's exactly, well, with absolute values, that's exactly the same. And then this just means that we would have this absolute value with a constant in front. So these three mean that delta H of W is constant times Fp minus Fr squared. Now, of course, we prefer the constant to be positive, because if the constant is positive, we have this picture. If a constant is negative, we would have a picture like that, and that won't be of much help because they can drift apart in the middle. Well, it will be slightly more difficult. The estimates will be slightly more difficult because they can drift apart of the middle. We'll have to check magnetization in the middle. But basically, there is sort of a hand-waving argument without calculation, which tells you that there is such a formula. We just don't know what is there. And maybe I'll just give you the second proof. The calculation. So let us just work with this picture. Maybe I'll draw it one more time here. So I'll just doesn't really matter what are the phases, but let's say that they were 1. No, it was 1 on the horizontal one, so it's 1, I, and so we were on where we were on white, so we go black on the left. So we go black on the left, so it's 1, it's then lambda, so it's then lambda inverse, then it's lambda. Now suppose that, well, let's say here we write, well, let's denote that P capital is f of P, is what we have written here. Then here on this edge we have a real part of that guy. So we have P plus P bar. Now if we here have R, which is f of R, here we have projection on lambda, which is which is R plus so what is it, lambda squared R bar. I have to divide by 2 probably, or everything, yeah, but let's say. And similarly here it will be P plus lambda minus 2 P bar over 2 and R plus I squared R bar over 2. So now what we had here, let's say, we have S plus S bar over 2, which can be calculated from this formula. So essentially, if we start writing Laplacian of H at the point W, so it's the sum of the differences like this, sum of the 4 differences. And for example, I mean, one can do either way one likes. So for example, one can do that this difference will jump twice like that, this difference will jump twice like this will jump twice like that, this twice like this. So we get a sum of a sort, so we twice, for example, we twice jump over this H, so we have to take twice the square of this guy, twice p plus delta minus 2 p bar over 2, well, absolute value squared, plus we have to jump over this H, so we'll have S plus S bar over 2 squared, but that we have to plug in S. Then we have to put this H, and this H will be projection of pi on I, so it's P minus P bar over 2 plus P minus P bar over 2 squared. So this is what I've written is the right half, and then there is a similar left half. So the important thing is that we get a quadratic form, in P bar, R bar, and after some tedious calculation you get that this is just P minus R absolute value. Yeah, of course here you don't, yeah, well, you, of course you, instead of absolute value you write number times its complex conjugate, and then you open the brackets, and then what you get is P minus R absolute value squared. So basically, when you open it up, you have a whole lot of terms of the type P squared, P bar, PR bar, etc. And it turns out that essentially everything boils down to this only. So all terms of the type P squared or R squared or PR, they cancel out. The only terms which are remain are P bar, PR bar, and that in principle also you can see because there is some symmetry. So there are one can bring symmetry arguments in the very beginning to say that you should get something like that with the constant in front. But it's a nice bonus that the constant is positive, because then we have two functions like that. Okay. So I don't want to go into calculation, so I wanted only to convince you that it can be done in a matter of, the question can be done in 45 minutes, and usually the second or the third time around one gets it correctly. So, but since a nice answer, one can convey there is a nice answer, so you sort of can self-check that it is okay. Also, of course, the one way to check what you get there, since you know that it's a quadratic form, just try what is going on when you put 0 and 1 here, or 0 and I, or 1 and 0, or I and 0, and if for 3 numbers it will be correct, then for 4 numbers it will be correct, and then you get the correct form. Okay, so this is our was one of our depths, and what I want to stress that it's actually nice in principle. One can also use this identity in the estimate, because essentially it tells you, so I will erase this. So the remark. So essentially it says that delta H is equal to number F absolute value squared. So when one can write delta H as a number F squared. But And of course you ask the question, well, okay, we have a function which is supposed to be harmonic, so that h is supposed to be harmonic, so why we have something non-trivial on the right? And it's because, as I said, f should be normalized by the mesh of the lattice. So what we expect to have is that f tends to 0, and f over square root of lattice mesh, I don't remember we denoted by epsilon, I think, it tends to something non-trivial. So actually, what we have here is really the thing of the order epsilon now f squared. So it's think of the order lattice mesh times a constant. So it can be used to ensure that so this identity can be used to ensure so this tends to 0 as epsilon tends to 0. So this can be used to show that that limit of h is harmonic. So we don't use it, but in principle one could have started from that idea. Okay. So now where we are with all the lemmas we have. So now the sort of proof of theorem. Now the theorem, what was the theorem? The theorem was that so reminder, the theorem was that if we have simply connected domain omega with 2 points A and B, and then we discretize with epsilon mesh to get domain omega epsilon, A epsilon, B epsilon. So we get some domain which goes something like that. So we get then the function, so we get the function f epsilon and h epsilon. So as epsilon tends to 0, h epsilon tends uniformly in omega away from A and B to a function h small, where h small is harmonic and h is equal to 1 on BA. H is equal to 0 on A, so just a solution of Dirichlet problem. So it's just a solution of Dirichlet problem. Maybe the best thing, and then f tends to gradient of h, but maybe the best thing is so that we can properly differentiate. We define. So so this Dirichlet problem is just imaginary part of a map phi to a strip of width 1. So or equivalently h is equal to the imaginary part of phi, where phi is the conformal map from omega to a strip of width 1. So r times 0, 1. Because the imaginary part is harmonic and 0 and 1. And what happens with f is that f epsilon over square root of epsilon, so it stands uniformly inside omega to square root square root of 2, I think. Yes, square root of 2. So we formulated this part of the theorem because we had only f. Now we have h, so there is also a first part. And first part we already have proved. So that was what I finished with last time. So proof first. So I'll just remind convergence H. So we have this thing that H B star is at most H B at most H W at most H W star, and this is subharmonic, this is harmonic, this is superharmonic, and this is again harmonic. And we also have HB star minus HW star tends to 0, the difference as epsilon tends to 0. And we have that HW star is equal 1 on the RPA, and H black star is equal to 0 on the RAB. So this all implies that all these three functions, four functions, they all converge to function h, which solves the Dirichlet problem. Because we have shown that the solution of the discrete Dirichlet problem tends to h, and here we have something which is close to the solution of Dirichlet problem. So the solution to the Dirichlet problem is, so if the difference between those two is of the order, let's say, k, then solution of Dirichlet problem is also at most k away, and it converges to the continuous one, so these two also converge. So one can compare, it's basically the solution to the Dirichlet problem, it will be in between those two. So let's denote a new thing. So let's say that this is h whatever h prime. So h prime a solution to discrete Dirichlet. Then clearly h prime is in between h w star and hb star, because it's has smaller boundary value than hw. It's 1 on one side and 0 on the other, whereas hw is positive, and bigger than hb because it's 0 also, but here it's smaller than 1, so it's in between them. And then, so this thing, it first implies that h prime converges to h, and then this implies that the whole path converges there because the difference is small. Now so is it clear? So it's just, I mean, we proved the convergence of the discrete solution to continuous one. And now the only problem that our things with which we work are not discrete solutions, they are approximate only. But they approximate up to small error term. And it's because of this picture that there is a subharmonic and subharmonic, and they squeezed like in a sandwich between two harmonic functions, and the harmonic solution to the Dirichlet problem which converges is also squeezed. So this solution converges, and then this whole pack, which is epsilon away, well, not epsilon, some small number away, also will be forced to converge. So there are two speeds. First, there is a speed with the actual convergence takes place for a nice solution. But also there is this thickness of this sandwich, which is properties of the Ising model. What is how that magnetization, how fast it goes to zero. So the speed of convergence will be the worst of these two speeds. But it will be basically some power of epsilon.
Sorry, I think I lost a bit. So what's the weakest statement on HB and IHW which is sufficient now? Does any convergence to any
for us, we know, I mean, it's clear, so it's immediate that we have this sandwich picture. So that is immediate. And it only uses properties of our functions. HW is bigger than HB because they have defined that you, to go from HB to HW, you increase. The upper one is subharmonic, the lower one is superharmonic. So you have this squeeze harmonic, subharmonic, superharmonic, harmonic. So that you have automatically. And then there is a solution harmonic which is in between them. And this solution is always converges. Now to deduce this, you use that, so here what we use is that the supremum of HW star minus HB star tends to 0. Or supremum of these two things tends to 0. So we need, well, on the boundary it's enough, so it's enough that it's supremum on the boundary of HW minus HB. So we have to show which is supremum on boundary of absolute value of f squared. So we have to know that absolute value of f squared tends to 0 on the boundary away from A and B. So we need basically that this away from A and B. So we need this away from A and B. So basically what we need to know that our curve is not space-fitting, that if I cut away, so it's clear that the neighborhood of A, it's a big probability that it visits an edge, because it has to, so if I take size 5 neighborhood, there are only 5 edges out, and it will go through one of them, so probability of visiting one of the edges is at least 1 in 5 for some of them, so the function is at least, square is at least 1/25. But if I go away, so what I claim that if I go away, then here f tends to 0, so the curve is not space-fitting. Basically, the probability to visit some point tends to 0. So we need that. So that's the only thing we need.
Okay, as a result on HB, we need only just existence of any convergence harmonic function. Because we don't.
Well, we use it not. Yeah, we need just any convergence. Yeah. So the convergence will be as fast. So there are two steps. So one step is how fast is the usual convergence, and how fast the usual convergence is depending on how you discretize the domain. And so there are these problematic points where you jump from 0 to 1. But basically, it's always a power law. Basically, it's always a power law in this case, because morally what can happen? You discretize the domain, you take one more step, so if you take one more step, the domain is epsilon thicker. So it's basically some power of epsilon change in the middle. So it's like if you have this domain and you have this harmonic function, then I said discretize differently and did it epsilon wide, and then I will have this harmonic function. The difference will be here of the order of epsilon. Well, in one-dimensional case, in two-dimensional, it's like, well, okay, but basically you never get worse than epsilon. And then, so this is this convergence, some power of epsilon. And then we have to say how close we are, because a priori, of course, it could have happened that our game went bad, and we have a picture like this, that the difference between this HB and HW is very big. So it's of order of 1. And then of course there would be no convergence. But here it is not, it tends to 0, and well, so essentially we only use the fact that the curve is not space-filling, or equivalently if you write it in terms of the FK model is that the cluster has 0 area, or if you write in terms of the Ising model is that magnetization is 0. If you are far away from the boundary, then you don't feel the boundary effect. So essentially, this also a power law. It says that if you are in domain n by n, then in the middle you feel boundary effects as some negative power of n, not more. Actually, Q is n to the power 1 over 8, but so that's the theorem of Kaufman and Anzeiger. So basically, yeah. So the remark here. Yeah, maybe in the second half actually I can prove it in the second half if need be. But remark that it's sufficient to use. Well, think like that. If I have a box, let's say 1 by 1, and the mesh is epsilon, and the boundary conditions are plus, and you take a spin at the center, that at criticality, probability that spin at the center is equal to plus minus 1/2. So this thing is smaller than, so this thing tends to 0 as epsilon tends to 0. So it's sufficient to use this. So you don't see the boundary if it's, and actually, so this is so that actually this thing is of the order epsilon to the power 1 over 8. So we even know the exact order. And this was first announced by Kaufman and Anzeiger. And they never published it, so they never written, but apparently it was found a few accidentally stumbled it in his archives a few years ago, and now they actually moved from Yale to Trondheim in Norway, and it's all digitized, so they actually wrote a paper and typeset it, but somehow didn't send for publication. And it was published by Yang in 1952, so that's a famous Chinese physicist who is a Nobel Prize winner, and he's actually still alive and well. He's 90, I probably have seen him somewhere. So he's 90 something, well, if he had theorems, famous theorem 63 years ago. So it's...
How to get this 1/8?
Sorry?
How to get this 1/8?
How to get this 1/8? How to get it 1/8? You know what? Let's maybe get 1/2 of the boundary, and yeah, okay. So there are well, okay. So then there are, of course, the CFT solution. So this is all unreaders, and then you can check. There are more recent papers by Dima and colleagues. So it's Chokak, Claire, is Europe. So they not only write this epsilon to the power 1 over 8, they also write constant in front, which is a conformally covariant constant. So if you move the spin inside the disk, the constant in front will change covariantly. Like, well, if you map it by map 5, it will change like 5 prime to the power 1 over 8. Let me just see. Well, we'll see. Yeah, okay. Yeah, maybe if How asks, so I'll just explain maybe then after the break. We'll explain that if you do the same thing on the boundary, so you do free boundary and you do half of it pluses, and you take a spin here, sigma x, then this probability that sigma x is a plus spin minus 1/2, deviation from 1/2, so this is of the order epsilon to the power 1/2. So on the boundary it's a smaller power than inside. No, it's like a smaller, bigger, I think I did it correctly, yeah. these two numbers after the break. Yeah, because in principle, with what we know, we can get them from SCD, etc. It's not a big deal. Well, I mean, yeah, okay. It's more difficult to actually prove it and get constant in front, but to explain where does it get, where it appears from SCD is fairly easy. So it's some dimension of SCD. Okay. So this concerns convergence of H. Now we have to pass to convergence of F, and that's maybe a good place to make a break, because I want to do it in 2 minutes. Yeah, so let's have a break. If U, W are white neighboring squares, and Z is the point in the middle, then so what was it? That H of U minus H of W is equal to imaginary part of F squared of Z divided by W minus U. And then there was a constant in front, so we were no, it's the other way around. It's the other way around. Yeah, so it was times W minus U or W minus U, and there was also, I think, a constant which was, I think, 2 here, like that, I think, square root of 2. Okay. Yeah, maybe square root of 2. Yes, square root of 2, I think so, yeah. I think it should be 2, but... basically... no, I think it's okay, yeah, that's what it should be. We can rewrite it. We can rewrite it as the image of F squared of Z is equal to, so let's just move everything else to the right-hand side. So it's H of U minus H of W over, well, let's say HW minus H of U. H of W minus H of U over W minus U, or times square root of 2 W minus U. And W minus U, it's basically a diagonal of, so the lattice mesh is epsilon, so W minus U is square root of 2 times epsilon. Yeah, everything is correct, yes, yeah. So here is the missing square root of 2. So this whole thing is twice epsilon. Yeah. Or maybe I can rewrite it as image part of F, measure part of square Z over epsilon is equal to 2 H of W minus H of U or W minus U. So this is basically derivative of H in this direction. So this is basically a discrete derivative, well, let's say in the direction alpha of H. Oh, it's I didn't. Yeah, I shouldn't have moved this from under the imaginary part. Yeah, I did. Yeah, how is better to? yeah, I should have left w minus u here because it's imaginary part of this. Yeah, so it's imaginary part of f squared of z times, let's say, so we have to leave it here. Imaginary part of yeah. No, because it was imaginary part of the whole thing. Just yeah, I want to reduce this. Yeah, let me. Sorry, so I'll just do it like that. So I'll do it without complex. Yeah, I was just going a little bit too fast. So let's do it without a complex derivative. So we divide. So we have this over absolute value of w minus u. Now there is what I wanted to do. So this I want to keep. I want to put. Yeah. Okay. Yeah. So that's. Yeah. So we'll do it like that. So this is twice epsilon. Yeah, so if I denote this vector alpha, I get imaginary part of f squared times alpha is equal to derivative in the direction alpha of h times twice epsilon. And maybe I put epsilon the other way around. Yeah, okay. So this will converge to twice the derivative of h small, which is the limiting function in the direction of alpha. Now, this is a bit of a tricky thing because we have this theorem. So this is, let's say, inside omega. So we have this theorem for harmonic functions. We have for discrete harmonic that they converge with their derivatives. And if you recall, we had this sort of funny picture. So we have to have control over derivatives of these functions. But since we jump between the same, at least we don't jump from one function to another, we jump within the same function, it can be controlled because our function is subharmonic, but it's squished in between two functions distance epsilon. So basically the total amount of subharmonicity can be bounded, so its derivatives also are very so they also will converge. So here there are basically two ways to deal with this. I don't want really so for harmonic function, which we denoted h star converges to a small, and the gradient also converges inside omega. And then we can try to prove that gradient of h black is approximately gradient of h star. So that's one way. So second way is just to do some precompactness, because basically if this thing converges, it has to converge to this one, because if a derivative converges to something, it has to converge to derivative of the function. So if h converges to h small, then should derivative of h have a limit, it would be derivative of h small. No way around it, because you can just integrate. So another way, second way, is just use precompactness. So well, one can, for example, find, so I have several bounds written here, but for example, one can show that for u inside omega, if I do L2 norm of f squared over epsilon, so this is what? This will be basically the sum, the sum over u of f squared, f over square root of epsilon, f squared over epsilon, that kind of thing. Basically, so what is, it's integral over u. Yeah, integral over u. Now, if we have this epsilon mesh, then basically every point is counted epsilon squared times. So this is sum over u epsilon squared f squared over epsilon. So this is sum over u epsilon, absolute value of f squared. And one can bound this by just an absolute constant, which is smaller than infinity. Just using the bounds on f, we can get from magnetization. Or something like that, or something like that, and then take converging subsequence. So either way, it's a technical thing. And either it's solved by, like for percolation, we do some a priori estimates and we show that there are converging subsequences, and for converging subsequences it had to be that, or we directly work with H, but we have this convergence. Now, this is better to rewrite in terms that we can write not H, but this phi. So basically, what we get there is sort of, imaginary part of f squared alpha over epsilon tens, inside omega to twice derivative in direction alpha of h. And if we rewrite it in terms of phi prime, then we'll get that just f squared over epsilon tens inside omega to phi prime, twice phi prime. Because basically h, so we use here that h is imaginary part of phi. So derivatives of h, they are just derivatives of phi. Well, the derivative of h in directions x and y are just real imaginary part of derivative of phi. So basically, this means that phi prime is what? So if it's imaginary, so it should be hy minus ihx, something like that. And we just apply this for alpha in x direction and alpha in y direction. So once again, either we work a little bit more and show that our subharmonic functions converges, or alternatively we do some precompactness, and if we have a scaling limit, what we get is that any subsequential limit, first of all, it will be it will have analyticity properties, and it will be that just because h converges to h, so h prime converges to h prime. And then this implies, by taking square root, that f over square root of epsilon converges to square root of 2 phi prime. So the important question you can ask now is why, if function converges, its square root of converges. Why it can be that on even sides we take one branch, on odd sides we have another branch. And this is because both of these things are analytic. So if you choose one branch, then it has to be the same everywhere. So basically, we basically know here, so if I denote it by A, we know that A squared converges to something, and we know that A is analytic. And then it will mean that A converges to the square root of something, which also is analytic. So everything is fine. So that finishes the proof of the theorem, and now I want to discuss a few ramifications, because it's very different from what we had in uniform spanning trio intercalation, is that mesh of the lattice figures here. And we have here not a conformal invariant, but something conformally covariant, because there is a derivative involved. So the first remark is that the limit is conformally covariant. So what I mean if there is a domain omega, and then there is a map phi to a strip, and then there is a domain omega prime, and there is a map between them, let's say G, and then there is a map psi here, then what I have, if I have psi composed with G equal to phi, then when I differentiate, I get that psi prime of G times G prime is equal to phi prime. So I get that the square root of psi prime of G times square root of G prime is equal to square root of phi prime. So I get this factor. So when I move from one domain to another, I get a factor which is square root of the map. Which is important, for example, when we connect to a SLE, because if we open the slit up and move by a map G, we have to factor out G square root of G prime. So it's slightly different from percolation crossing probabilities, and that we'll be doing in a minute. Well, the second remark is obviously that f tends uniformly to 0, but f over square root of f tends to something. So basically, f is of the order of square root of epsilon, normally. So basically, f is sort of a, if you remember, it's a probability, if I give a direction, to go with even number of turns, minus probability to go with an odd number of turns. Well, let's say, yeah. So if I give even minus odd. Which is, of course, strictly smaller than probability just to pass with any number of turns, because I subtract two things. What is the probability to pass with a fixed number of terms? It's basically dimension of the corresponding SLE. So we haven't got an SLE yet, but basically this should be epsilon to the power 2 minus dimension of the corresponding SLE. Now we already know that it's SLE, we'll have SLE 16 over 3. So the dimension is, what is the dimension of SLE? It's 1 plus kappa over 8. So it's 1 plus 16 over 3 times 8. So it's 5/3. So this is actually epsilon to the power 2 minus 5/3, 1/3. So there is which is bigger than epsilon to the power 1/2, but just slightly so. So it's kind of an interesting thing which we have seen already in percolation, that these two things, their main contribution, their main order will be epsilon to the power 1/3. But it cancels out when you subtract, because it doesn't see the boundary, it only sees the geometry of the plane. And the next term, square root of epsilon, it already sees the geometry of the boundary and how many times you twist it. So it's the usual thing if you write such vertex separators, that the first term just sees the geometry of the plane, and then, so for example, if we do it, it cancels out because it doesn't care how many times you twist it around, but the next one sees already the boundary of the domain. So this corresponds to, so this is, so it's from the omega, and this is from the geometry of the plane near our point. Okay. Now there is a specific point where you cannot go twisting. On the boundary you cannot go twisting, so on the boundary everything is okay. So it's the next remark. On the omega, no twists. So let's assume that there is a straight interval. So assume that we have a nice domain. And when we approach boundary here, no matter what we do, we don't have any twist. So there we have that f of, we have what? We have on one hand that f, just probability that you touch the boundary is exactly equal to f, or let's say absolute value of f. But then this we know that this is of the order square root of epsilon. So this we know this inside omega, but and obviously it's not true near A and B, or it's not true if you have a fractal boundary. It very much f can go up and down because f is derivative of a square root of this map. So it's so let's say f is approximately square root of epsilon phi square root of phi prime. So if you have this crazy fractal boundary near it, phi prime can go to 0 or blow up. But near straight boundary, phi prime will be nice and bounded just because by Schwarz reflection you can instead the map. So this is like constant near straight boundary. So just use the Schwarz reflection to get inside domain. So this is square root of epsilon. So what we get, that probability that we touch one square, or for a silly thing of the order epsilon square root of epsilon. Well, in particular, this can be written in the way that Hausdorff dimension of where SLE 16/3 touches well, straight boundary. So it's straight. So it should be equal 1 minus this exponent, which is still 1/2. So this is kind of a byproduct that our curve, we don't know its dimension yet because our observable, so the dimension is 5/3, but our observable gives us a different number. It gives 1/2, so it gives 3/2 because it doesn't calculate because there are cancellations. But on the boundary there are no cancellations, so on the boundary we see the dimension. Now, what is this? So probability. So this square root of epsilon, so this is probability that the loop touches, well, let's say again, straight boundary touches this. So this is in a loop model. Let's rewrite it in FK model. So in FK model, this is just the probability that the cluster from below goes to this point. So for the FK model, you have this wired bottom, and it's probability that cluster from below goes to the top. So let's say X. And if we rewrite it in the Ising model, so in the Ising model, it's a probability that, so if this is X, well, let me just draw probability that spin of X is equal to plus minus 1/2. And this is with the boundary conditions where it is free upstairs and O plus downstairs. So this was this bijection between FK models and spin models. You remember that how spins deviate from the mean, it is the same as how clusters propagate in FK model. So the magnetization in the Ising is just the probability of connection in FK.
Question.
Yes.
The things we are doing in these remarks, are there something that is known rigorously already?
Yes, yeah. Look, there are, well, let's say there are slightly different things. Let's say the first remark is rigorous. It just says that, look, we got something conformally covariant. The second remark is completely rigorous, only we have not yet prove that it's a Silly 16/3. We will either in 10 minutes or in 1 week and 10 minutes. So it's that will prove we'll have unobservable. It's basically the same machine. You kick it and it starts and it spits out the number kappa. Now, I mean, the only difference is that phi is conformally covariant. So this is completely rigorous modulo 16/3. Now, this is just completely rigorous model what everything I said. It just we proved convergence inside the domain. But if I take exactly straight line, you can do Schwarz reflection even in the discrete. If you have something smooth, it's a bit more difficult, but you can do it. If you have a fractal, it's wrong because phi prime might blow up. So this is completely rigorous. So this is how answer to your question that where 1/2 comes from. So here it comes from our calculations very rigorously, very nicely. Now 1/8. Let's discuss 1/8. What about magnetization inside? Well, let's try the same thing. So we try the following picture. So we have basically plus here and free here. It's more or less the same whether you do, if you have all free, then there is no magnetization. It's symmetric, so everything is fine. You can do O plus, but then you have to start a Silly somewhere. You have to, so we need a free part, but it can be just one hexagon, so it's not really important. And there is a point Z inside, so probability in the Ising model, given this boundary condition that spin at Z is equal to plus minus 1/2, it's probability in the FK model that Z is connected to the bottom arc. FK is that Z connected to the, so if it was AB, to the arc AB, to the arc AB. So how do we write it in terms of loops? Well, it gets a little bit tricky in terms of loops, because basically in terms of loops what we have this one SLE curve, and then we have a bunch of, let's say, a bunch of loops. So this yellow part is everything in between. So what you would call a gasket, so it's kind of you take everything below our interface and you cut out all the loops. So you get kind of like counter set, like Swiss cheese counter set. Only the difficulty is that these things, they are self-touching. So it's normally you draw these Swiss cheese type sets, which just is a round disk and round disk holes. But here it's like fractal set, fractal hole, so it looks more complicated. So it's basically, one can be written that it's of the order epsilon 2 minus Hausdorff dimension of FK cluster, or epsilon 2 minus Hausdorff dimension of this loop gasket. And it all, of course, we do for let's say Q equal 2 or kappa equals 16 over 3 if we to believe that we'll calculate it to be 16 over 3. So it turns out, bless you, that this thing is 15 over 8. So this is not the subject of this course, but the way Wendelin discussed how one can do calculation, one can calculate the dimension of a SLE curve is 1 plus kappa over 8, and one can deduce a formula for dimension of FK cluster. It will be quadratic in kappa, and it will give here 15 over 8. So this is epsilon to the power 1 over 8. So it's 2 minus 15 over 8. It's epsilon. So in SLE, the number which appears in the SLE theory is not 1 over 8, but it's complement to 2, which is dimension of some sets which are related to SLEs. So that's the answer to your question. So in principle, this Young's epsilon to the power 1 over 8 can be proved with a SLE by this way. And Young did boundary conditions O plus, and we do half plus, half free just because we need to run a SLE. For it doesn't matter. If it's O plus, we change 1 square to free and run a SLE, very small one, but we still get the same result. So it's not. And it, again, the final numbers like 1 over 8, 15 over 8, they appear just from SLE calculations from stochastic calculus. Or alternatively, you can do it, I don't have time. Челкак, Angler is Europe. So alternatively, what you can do, so we have this function of z, f of z. So one can introduce multi-point functions like that. One can punch a few points and ask what are the probabilities that interface passes through them and assign some signs. And from such multi-point functions, with enough with enough skill, you can create other things, including spins. But it becomes more and more complicated. So it's very roughly it's what I said, but in what I said there's much cheating. It's more complicated, but maybe next time I'll just say a few more words. Okay, so that's about 1 over 8. Now what else I want to say here? Yeah, okay. Now let us. So we have one more lecture next week, and then we'll have to discuss the modality of the exam. Now, in what remains, I want to prove that it's indeed 16/3, and maybe say a few words about how other things are done. So let me maybe indeed prove that it is 16/3. The theorem, this interface in FK model Q equal 2 converges in PC, converges to SLE 16/3. Well, in domain omega epsilon with points A epsilon, B epsilon, converges epsilon goes to 0 to SLE 63 in domain omega AB. So first proof, we need some a priori estimates. So for example, one I quoted about the magnetization, that magnetization tends to 0, and so it's not space filling, it's enough. And in a sense, what we are doing here with square root of epsilon, it kind of shows that one can do this from our reasoning without appealing to Ansager. But anyway, so let's just move it aside. Some a priori estimates imply precompactness so we can choose converging to a Loebner chain subsequence, and it's sufficient to prove its limit is SLE 16/3. Now we have a martingale. So F is a martingale for the discrete thing, because just of the way it is defined, it's a probability that this interface goes from some point. So if we condition on this interface starting like that, then it's just the same thing conditioned. So it's indeed is a martingale with respect to interface. Then it means that its limit is this square root of phi prime, is a martingale with respect to our Loebner evolution. So let's map to half plane and do the very fast calculation. So we have this curve gamma, so it's a subsequential limit. And there is a map Ft of z, which is z minus wt plus twice t over z plus small order terms at infinity. Well, gt, always for denoting. So we stop at time t, and we have this martingale well at point z, martingale at point z in this domain omega t, well, in the domain c plus minus gamma 0t at point z, is expectation of the values of c plus of z is expectation of the values of a martingale when the curve is drawn. Now martingale is square root of phi prime. So which maps half plane to a strip? So how we want to make this map? So who does it? Which function maps it so that 0 and infinity go to endpoints? Because this is our setting, so this is a and b is equal to infinity. So we want a map which sends 0 to minus infinity, infinity to plus infinity, and which sets. So basically, it's clear that it should look something like this. So who does it? The most sort of basic function in complex analysis. Well, I think it's a good time to stop for today, if everyone is tired. So what is the complex function which maps half plane to a strip? Of course, it's not some power, because powers like power 2 doubles the angle square root, it halves the angle. So if you have an angle 180 degrees and you get angle 0, it's not a power, it's something else. So you should search among like sines and exponents and all the things like that.
I mean, I know that it's log, but I'm still trying to write down the stuff.
Ah, well, it is a log. Yeah, okay. So it is the logarithm.
I'm just still trying to figure out just what's going on before that, so I thought it was a little early to.
Okay. So it is logarithm, obviously, because so if you take point r e to the power I theta, then logarithm of that will be a logarithm of r plus I theta. So this is I theta lines, and this is yellow logarithm r lines. So logarithm maps half plane to a strip. So what we have here square root of logarithm z prime. And what we have here, we have expectation, and now martingale we have to map our thing to half plane and then map to a strip. So to a strip it's mapped by logarithm. So it's basically expectation of square root of logarithm of gt of z prime. Okay, bless you. Now, what is the derivative of logarithm? It's 1 over z, so it's square root of 1 over z on the left. Now, what is the derivative of the logarithm here? So you should get 1 over g, and gt prime of z in the denominator. Here you can write expectation of these things. So gt of z is z minus wt plus 2t over z plus small order terms. gt prime is 1 minus 2t over z squared plus small order terms. Actually, we can immediately factor out z, so we can do like that. Times square root of 1 over z, because it's also what we have there. Now, of course, it's a game of sort of formally working with Taylor expansions. So what we have here is square root of let me think. So 1 minus 2t over z squared. So that's contribution of this guy. Now this guy will contribute the same thing with plus wt over z minus 2t over z squared. And also it will contribute, let me think, wt squared over z squared. With what coefficient? So it will be so 1 minus 1 over 1 minus delta is 1 plus delta squared. Yes. So just that, yeah. Plus small order terms. So it's the square root of 1 plus wt of z plus wt squared minus 4t over z squared plus small order terms. If not for square root, we could have written that w is a martingale and wt squared minus 4t is a martingale, so w is 4 times the Brownian motion. But there is a square root. It will change a bit the constants. And actually, if you put not square root, but a different power, you will also get some SLE, but not 16 over 3 another. Unfortunately, we only can do it for one model with a square root. So this, I'll just write the result. So it's expectation square root of 1 over z we always had. And then this expands as 1. Plus 1 over 2z wt plus 1/2, 3/2, 3 over 8 z squared wt squared minus 16 over 3 c plus small over the terms. So the conclusion is that if we just start to stop it at times t and s, not at times 0 and t, we'll get that wt and wt squared minus 16 over 3t are martingales. So by the Levy theorem, wt is square root of 16 over 3 Brownian motion. So the number 16 over 3 arose from a specific observable. It's just a number which pops out in calculation here. If, for example, I am to change here power, not square root, but let's say put power sigma for some other value of sigma, then I would get not 16 over 3, because the last step would be different, but some other number. And conjecturally, if you do like 3-state POTS model, then you should have power 1/3. And it should also work similarly, only we cannot do it on the discrete level. And then you would get some SLE. You would get some SLE, which is for thirds. No, for 1/3 it should be percolation. Yeah, for 1/3 you just get SLE 6. But yeah, so it's okay. So this is the end of proof. So the thing I put under the carpet is the pre-compactness, but in principle we discussed those things long enough. But otherwise the proof is exactly the same as for percolation on UST. Just one parameter is enough to control SLE. Again, one should think of it as if you are driving this car, and if you observe from one point what it is doing, it's enough to reconstruct the whole trajectory. So the only difficulty is that you have to solve nonlinear Loebner equation to reconstruct the trajectory, because you reconstruct easily WT, and then to reconstruct the curve you have to solve nonlinear Loebner equation. Okay. So now, so we'll have last lecture next week, and then we'll discuss a bit modalities of the exam. Okay, so thanks.